Good morning, students. In today's class, we'll start actually what is actually the meaning of electrical conductivity of semiconductor. So you had already information regarding in the uh, about the electrical conductivity of the semiconductor. So before that, we just have a recap of what we studied in the last class. So when you just see the last class, in the last class we studied about the density of electrons in the conduction band and also the density of holes in the valence band of the given semiconductor. And we conclude that there exist the there exist two types of charge carriers in the semiconductor. So as in the case of conductor, we find that only one charge carrier is there, that is electron. But in the case of semiconductor, there are two types of charge carriers. So in this particular scenario, what we are doing here is that we want to know how these charge carriers are moving inside the semiconductor, right? So the theoretical statement has been just now told to you that should be verified mathematically. What is the basic formula which is resembling the charge carriers of the semiconductor? So in today's class, we just have the very clear idea regarding the type of charge carriers that is the inside the semiconductor, and also we'll just discuss the basic mathematical relationship uh, in the semiconductor in order to see that the semiconductor there are two types of charge carriers. So we just have a very clear idea regarding this by using the mathematical relationship. So one thing that we need to understand in this particular topic, that whenever the movement of charge carriers are there, either it is due to the holes or the electrons, now that can be related by a mathematical relation. So now we just have a very conceptual, what you can say, conceptual method to know the mathematical relation of this charge carriers, right, which are residing in this semiconductor. Now, this is basic thing that we need to understand, right? So now, before going to the electrical conductivity of semiconductor, a few things, a few parameters you need to understand, right? Whenever the electron or current is flowing inside any substance, definitely that particular electron will acquire the character of that particular material. So we just say now, we don't say only current, but as it is acquiring the character of the material, we just now will say that that is current density. So basically the current density, the moment of the, first we'll just discuss about the electrical conductivity of the semiconductor is due to two types of mobilities of the charge carriers. What is the meaning of what you can say? The mobility is nothing but it is the velocity which is acquired by the electron or the holes, right? So we just say that the mobility, that is called mobility. Mobility is movement, right? So what type of movement is happening? The electrons and holes are moving from one region to the another region. So that is called the mobility. So that mobility value, we will just discuss in this mathematical relation. You can just see the screen where you'll have a mobility relationship of the electron. It has been given in the PPT. Right now, this particular slide. So now the movement of the electron is in the presence of how the electron will move when you apply some amount of electric field. So the movement of electron in the presence of electric field is given by the relationship of the current density, that is J is equal to sigma into E, right? Now, so you can see J is equal to sigma into E, and sigma is nothing but J by E. So where J is nothing but the current density and sigma is the conductivity, and E is the, you can say, the electric field. Now, the conductivity is given by J by E. See, the conductivity sigma, which is denoted by sigma. Sigma is equal to J by E. Now, what is J actually? This is already when there is a relationship. The current density is given in the lower classes. You had information that J is nothing but NEVD, right? This is the sigma is equal to Instead of J, we can write NE VD by E. That is equation number 1. This is the conductivity mathematical relation of conductivity, that is sigma is equal to NeVd by E. Now, what is mobility? Just now I told you that mobility is nothing but it is the velocity which is acquired by the electron or the hole, right? So the mobility is related by the mathematical relation mu is equal to Vd by E. Right? Now, what is Vd? Vd is nothing but mu. In the case of electron, now if I talk about mobility of electron, I will just write mu suffix n into E or mu suffix E into E. Right? Now, so we just substitute this value in our basic equation. Now, the electrical conductivity is given by Ne into mu. So the current density of the electron due to the drifting of the charge. We say that if there is a movement of charge carrier and particularly the movement of electron, if I talk the movement of electron, then I just say that that is in the presence of electric field, the movement of electron is nothing but it is it is given the name as drift. So J suffix n drift is equal to Ne mu n into E. So you can just see this previous slide. You can see J is nothing but sigma into E. Right? Clear, everybody? So what is sigma? NeVd by E. That just now. So now Jn drift is equal to, that is the reason that we're writing here Ne mu n. So J is equal to sigma into E. So sigma value is Ne mu n into E. So now we got information regarding the drift of the charge carriers in the presence of the electric field. So the movement of charge carriers with respect to the electron, it is given by Ne mu n E. And then we'll write Jp also. Why? Because the charge carrier, movement of charge carriers in the semiconductor is not only due to the electron, but also due to the holes, right? So now, see, in case of semiconductor, drift current density due to the holes, as just now I told you, J suffix B drift is equal to P mu B E into E. So then the total drift density, current density is given by Jn. J suffix n is nothing but it is the movement of charge carriers of the electron. So here it is a movement of holes, right? So now when I just replace that J drift total J value, the current density or J drift is equal to N mu N E E plus P mu P. Suffix mu P is suffix E into E. So when we just take small e and capital E, right, into common. So N mu suffix N plus P mu suffix P. Now, so the conductivity value, you already know J by E. So you can just see this, right? So if you have any doubt, J is equal to sigma into E. Sigma is the electrical conductivity, J by E. Yeah, just remember that conductivity is J by E. So J by E. So J drift is, we got this value. So this capital E and this capital E will get cancelled when it's come to this equation. So what is remaining? E n mu n plus EP mu P. Understood, everybody? Right. Now this can also be written as E n mu E plus EP mu H. Right. So H, why we are writing instead of P? You can write P or H. So it means that we are talking about the mobility of the holes. Mu E, we are talking about the mobility of electrons. So by for now we got an information, very clear information regarding the current density of this. So our basic equation for intrinsic semiconductor. So J drift is equal to what I can write here. Sigma E drift is equal to NIE into mu E plus mu H, or else mu N, mu suffix N plus mu H. Now what I'm doing here is that now we just replace this NI value we already got. What is this NI value? We got in the previous equation. That is the carrier concentration we have calculated. If you just remember, so if you don't remember, I will just show you what is the value of Ni we got, right? The previous slide. See the Ni value what we got previous for electrical conductivity, right? Just now I will show you. For intrinsic semiconductor, we got this value. See, Ni value is 2 into 2 pi kt by h square whole to the power of 3 by 2 me asterisk me to the power of asterisk mh asterisk 3 by 4 exponential of minus eg by kt. This is the value of Ni. Clear, everybody? Right? This is a value of Ni. We are just replacing this value in our equation. We can just see Ni is equal to 2 into 2 pi kt by h square 3 by 2 me asterisk mh asterisk 3 by 4 exponential of minus eg by kt. So what we are doing is that we are just replacing this value in our basic equation. What is that basic equation? See, we are just replacing it with this equation. Sigma I drift is equal to n suffix I e mu mu n plus mu p or mu e plus mu h. But the same thing now. We can just write this as sigma is equal to, so this is value is what I will write this as E, so E, right, mu h or n, you can write anything, mu p. That's what is that equation? 2 we are writing here. I'm writing 2 here. 2 into 2 pi 2 pi kt by h square whole to the power of, right, 3 by 2. Now what is remaining here? Me. See, you can just make a note of it. So n asterisk m h. See, that is the reason that I'm not writing, doing any written part here. This is the reason that I'm making these slides here, right? So exponential of right, you can just see minus Eg by 2 kt. Now this is the value of you can say the electrical conductivity. So now what we are doing is we want to simplify this equation. So how we need to simplify this equation? So for intrinsic semiconductor, right? And what I'm doing is for intrinsic semiconductor, N is equal to P is equal to Ni. You already know this. Now what I am doing here is that sigma for intrinsic semiconductor is equal to, so A, instead of all these things, see, instead of all this thing, what I'm just writing it as, see, this particular part, this complete part, I'm writing it as A, right? So writing all this thing is writing, right? What is remaining? Exponential of minus Eg by k. Exponential of minus exponential of minus Eg by 2 k t. So what you can infer from this equation now, we can just make it more simplified by taking log on both sides. See, taking log on both sides. So what I can write here, log, which for simplification purpose we are using log here, right? So log is equal to, what will left then? Log of log A minus Eg by kt. So right, exponential and this will get cancelled. So Eg by 2K. So why I'm making it random? Why not we can have a separate slide for it? Why? Because see here, we just replacing. We want to get an information regarding the intrinsic semiconductor. So what we got Ni value, right? Ni value. So we are just writing this particular part as A exponential of minus Eg by Kt. So taking log on both sides, log of sigma I is equal to log A minus Eg by Kt. Okay. Now this is the way that what this infer. Why we have done this all this thing? Why? Because when you just plot a graph, so when you plot a graph between this conductivity value and the temperature inverse of the temperature, so only the conductivity will be increasing, see, inversely proportional. You can just see that the conductivity is inversely proportional to 1 by T. So the conductor, what we can infer here. So as we plot a graph between, see, when we plot a graph between 1 by T and in terms of Kelvin, right? 1 by T on x-axis and the log, right? Log, right? Log sigma I on the x-axis, we will get this type of graph, right? So as you increase the, what you can say, the conductivity is increasing with the because so you can just see this particular graph. We can know the how this conductivity value is changing, right? So now this is the case for the intrinsic semiconductor. So now we got an information, right? How the electrical conductivity of the intrinsic semiconductor varies with the temperature. Now in the examination, he'll ask you what derive the expression for electrical conductivity of the semiconductor. So the electrical conductivity of the semiconductor can be calculated from this particular, you can see this starting from this slide. So now this is the way how we can know the character of the conductivity of the electrical conductivity of the intrinsic semiconductor. Here we are very much interested in the electrical conductivity of intrinsic semiconductor. So just now we have calculated the electrical conductivity of intrinsic semiconductor. Now when we go for the further, so what we are doing here is that we want to have a very clear information regarding what is happening when this p-type semiconductor and n-type semiconductor are joined. So when p-type and n-type semiconductors are joined, so it is forming a junction, and we say that it's called p-n junction, right? So that p-n junction, we'll just see a small video regarding this p-n junction, right? So we'll share that video also in the last part of my class. So now I think that you got some idea regarding what is actually semiconductor, how the semiconductors have been classified, how many types of semiconductors are there, and then how the movement of charge carriers are there inside a semiconductor. So that also we have calculated mathematically. And what are the different type of charge carriers? So two types of charge carriers, that is electrons and holes. Now what we are doing here is that, just a minute. Just clear this. Right. Now, when you just see this, right? Now we are not interested in this. This is what we are doing here is that now when we go to the Hall effect, just now in previous classes also we have discussed the Hall effect. But here also we are discussing the same Hall effect, but we haven't discussed about the derivation part of the Hall effect. Right? We need to calculate Hall coefficient. How we are going to calculate the Hall coefficient, I will just tell you in this particular class, and at last we'll share you the p-n junction diode. What is actually the meaning of p-n junction diode, and how many types of p-n junction diode, and what are the different applications of the p-n junction diode. So you just have a very clear idea regarding this, right? So you are, as you know, that when a magnetic field is applied perpendicular to a current carrying conductor or a semiconductor, so voltage will be developed across the specimen, and these voltage will be developed. Whatever the voltage has been developed, that will be definitely perpendicular to the both current and the magnetic field. And this phenomena, we just say that is called Hall effect. This is a, oh, okay, and this developed voltage is also called voltage. Now, this particular aspect is actually Hall effect. So when you come to the lab also, you'll have a Hall coefficient. How to calculate Hall coefficient? Experiment by means of an experiment. We'll see that how we are going to calculate this Hall coefficient, right? So now in this particular class, we just derive a derivation or an equation related to the Hall coefficient. So let us consider a thin rectangular slab which is carrying current in the x direction, and if we place a magnetic field which is in the y direction. See what we are doing. We are taking a thin rectangular slab, right? Rectangle slab of this of either it may be a conductor or it may be an insulator. So in the form of a rectangular slab which is carrying current, right? Let us consider the current is carrying current by this rectangular slab is in the x direction, and magnetic field which is acting on this particular slab is in the y direction. And definitely when we talk about x and y direction, magnetic and electric field, they are exactly perpendicular to each other. You already know. So now then there will be a voltage will be developed between this, I will show you this, between these spaces. Voltage will be developed. See, what we are doing is that we are taking a rectangular slab, and this rectangular slab is nothing but it is a semiconductor, and we'll know why it is a p-type or n-type. In the derivation, I will explain you. While seeing the derivation, I will explain you, is it a p-type or n-type, right? So now rectangular slab which is given now in the opposite direction is voltage is generated. So you can just see this schematic diagram. So what is actually the force which is acting with respect to the magnetic field? You already know that S is equal to Q into B and Q into VD into B. Now this is the velocity of the charge carriers, which is multiplied with the magnetic field. So the force is given by Q VD into B. So now the electric, the force which is acting on the electric, what you can say, the charge carrier, which is residing due to the electric field, is given by F is equal to Q into EH. Now, so this is you can, if you remember the intermediate. So in J.J. Thomson experiment, what is happening when magnetic field? What is the force which is acting on the what you can say when magnetic field is there, and what is the type of force which is acting when the electric field is there? So in the same way, since you can see this diagram, so there is a magnetic field and also the current, right? So here, so that is the reason that we are writing F is equal to Q into VD into V and F is equal to Q into E. So now what we are doing is that at the equilibrium position, the magnetic deflecting force on the charge carriers is definitely balanced by the electric forces due to the electric force. So there are two types of forces which is acting on the rectangular slab, that is due to the magnetic field and also due to the electric field. So that is given by Q into VD into V is equal to Q into EH. So now we can say this Q and Q get cancelled. This is the charge, right? So EH is equal to, right, EH. So why we are writing E suffix H? Now that is actually the electric field which is produced due to the Hall voltage. So now E suffix H, now EH suffix H is equal to VD into V, and VD is what? A drift velocity. I told you in the previous slide also, whatever the current which is flowing, that is called drift current, right? So here the drift velocity, V suffix D is nothing but a drift velocity, right? So here, so the relation between the current density and the drift velocity is given by VD is equal to J by, you already know J is equal to NE. So J is equal to NE, J is equal to NJ by VD is equal to J by NE. So we'll just write that VD is equal to J by NE. So where N is the number of charge carriers per unit volume. What is N? The number of charge carriers per unit volume. Just writing that as N. J is the current density. So EH can also be written as, you already know this, EH is nothing but VD into V. So EH is equal to, what is VD value? Just now we had a relation J by NE. So drift velocity is nothing but the J by NE. So VD is equal to J by NE into V. So what I'm doing is that 1 by NE into J into V. So what is this 1 by NE? That is called actually R suffix H. That is called Hall coefficient. So RH is nothing but Hall coefficient, which is equal to 1 by NE. Now RH will be equal to EH by J into B. So what I am doing here is that the RH is nothing but EH by J into B. So Hall coefficient is equal to EH by J into B. So now this is the value of Hall coefficient from the basic diagram, right? So now EH is nothing but BH by B. So where D is the width of the slab and RH you can write, just now we have known this, RH is nothing but EH by J into B. So EH is the electric field which is due to the Hall, and J is the current density, B is the magnetic field, you already know this. So RH is equal to H by J into B. So RH is equal to 1 by JB. EH, you already know, VH by D. So just VH value, we got RHJBD. And if A is the cross-sectional area of the current density, so what we can write, current density is actually equal to the current per unit area. So VH is equal to RH into I by A into B into D, where now this D is nothing but it is the width of the slab and A is the cross-sectional area. So width of the slab by cross-sectional area, we get this as VH. RH is nothing but VH into, instead of this D by A, what you can write, L, where L is the thickness of the sample. So D by A can also be written as capital L, that is the thickness of the sample, by I into B. Now this is the value of Hall coefficient. That is also we are having the experiment also, wherein we'll find out the mobility of the charge carriers, and also we calculate Hall coefficient and so on. So that is a way how we can obtain mathematically a relation. We have obtained a mathematical relation of the Hall coefficient. So definitely, I think that you had a good information regarding what is actually Hall coefficient and Hall. What you can say, a different mobility of the charge carriers and conductivity of the charge carriers. So if you have any difficulty, definitely we'll try to again I repeat this particular class with more ease for your understanding. So right, with this we'll just show you the video regarding the PN junction there. Just now we have completed the complete information of the intrinsic semiconductor. So here I'll just show you the video now.
The diode is a mainly resistive, nonlinear, passive electronic component with two terminals whose function is to allow the flow of electric current in one direction and virtually block it in the opposite direction. The two diode terminals are called anode and cathode. The electric current conventionally goes from the anode to the cathode following this direction. Opposite polarization of the diode will oppose a virtually infinite resistance. The diode blocks the current, reducing it to zero. Diodes are passive electronic components. In fact, they do not introduce energy into the circuit in which they are inserted and do not require an external power supply apart the input itself. There are many kinds of diodes depending on its use. They can be used in various electronic applications, and they indeed are an integral part of many electronic devices. JIS, in its catalog, offers a wide range of diodes of the major manufacturers. But how is a diode made? We can see that here inside is a semiconductor material. In this specific case, silicon. Theoretically, pure silicon crystal has no free electrons in conduction band. For this reason, the silicon in question has been doped. For doping, we mean that the impurity inclusion is made by diffusing of certain elements. In general, this is obtained by using a very small percentage of atoms spread within a silicon crystal lattice. These impurities, even in negligible amount, change dramatically the crystal electric behavior. These atoms are called donor atoms, since they yield electrons to the crystal lattice of silicon. This creates two distinct parts within the diode with two different charge levels. One part is doped in order to obtain an excess of electrons, and therefore it is negatively charged, while the other is doped in order to obtain an excess of holes and is therefore positively charged. We will call N the negatively charged part and P the positively charged part, thus distinguishing the so-called PN junction. Now we can see that in the N part of the diode, there is a majority of free electrons, while in the P part there is a majority of electron holes, which are the lack of an electron in a position where one could exist in an atom or atomic lattice. In this situation, the part N will have a tendency to release excess electrons, since these will naturally move towards the holes available on the P side. So the border region of the P side is slightly negatively charged, and the border region on the N side is slightly positively charged. A current, called diffusion current, will flow between the two parts and will try to balance this difference in the charges. We can thus see the so-called depletion zone. As there is a positive and negative charge in this area, an electric field will be created which will go from the cathode, K, towards the anode, A. This electric field causes the generation of another current, the drive current, which will try to balance the previous diffusion current. In case of an electric field, an electrical potential will be created and consequentially a barrier potential. The barrier potential is created when the electric field opposes a further migration of electrons from part N to part P. This phenomenon creates some sort of barrier against the flow of electrons. This barrier value is usually around 0.7 volts for silicon. We here now connect the cathode to the positive pole and the anode to the negative pole of a current generator, in this case a battery. By doing this, an inverse polarization or an inverse bias condition is obtained. The electrons and the holes are attracted in such a way to polarize the PN junction to increase the depletion region and consequentially prevent the flow of current. The effect of reverse polarization is to enlarge the depletion region. If we try instead to connect the positive pole of the battery with the P side of the diode, the situation changes completely. The diode will be in a forward biased condition and the depletion region will shrink. Supposing now that our battery has enough voltage to overcome the potential barrier, this will cause the movement of the electrons driven by the electric potential imposed by the battery. When the electrons cross the potential barrier, their motion no longer meets resistance and will thus more easily occupy the holes in the P zone. Now, the electrons that have moved from the N side to occupy the P side holes, due to the attraction of the positive pole of the battery, will move further going to occupy the nearby holes and so on, until they flow through the external circuit. This condition is known as direct polarization or forward bias condition of the diode. In a nutshell, the diode behaves like a non-return valve, only in this case the flow is not represented by water but by electricity. Now, let's try to vary the input voltage and observe the diode response. With inverted voltage, we can observe a negligible current. In direct polarization and voltage lower than 0.7 volts, a negligible current is observed. But as soon as this potential barrier is overcome, there will be a strong increase in current. In any case, we note that the voltage across the diode cannot exceed 0.7 volts very much, even in the case of a high input voltage. This depends on the forward bias condition. In this case, the diode places little electrical resistance. In the reverse bias condition, if a very high voltage is applied, the diode could be damaged due to the rapid increase of the current for small increase of reverse voltage applied. The diode characteristic of running the circuit in one direction only can be applied to many electronic devices, such as the rectifier bridge. In the positive half, the circuit will run the current as shown.
Thank you, everyone. Thank you for your patience.